So from the discovery that light had properties that only waves can have, to figuring out what kind of wave light was, took many decades. And what we know now is that what light is an electromagnetic wave. What that means is it's changes in the electric field, and the electric field can go all through space. It doesn't need a medium like air or water to travel in. The electric field is everywhere, and that's why the light can travel through space and through a vacuum. And what happens is when you have a changing electric field, that causes a changing magnetic field, and a changing magnetic field causes a changing electric field, and so the wave just carries on forever. What that means is that light is a transverse wave. The electric field is actually moving up and down perpendicular to the direction that the light is traveling. And it also means that light has something called a polarization. And all polarization means is that if the electric field is going up and down perpendicular to the way the light's going, it must be going in a particular direction. It might be going up and down, it might be going left or right, or something in between. Now light has two things going transverse to the direction of motion. It has the electric field and the magnetic field. And they're not both going in the same direction, they're actually at right angles to each other as well, and so we have to make a choice when we're defining things. And for light, we typically define that the direction of the polarization is the direction that the electric field is going. So if we have a light wave traveling in this direction, then we're going to have an electric field going up and down in one axis, and a magnetic field going in and out on the other axis. In this case, we would talk about the polarization as being up and down. Now, electric fields come from charges, and so changing electric fields come from moving charges. And so the easiest way to make an electric field that goes up and down is to have electric charges go up and down, and the easiest way to do that is to have something like an antenna. So in an antenna, you apply an oscillating voltage, which causes the charges to go up and down, and they emit an electric field, and then over time that travels on and gives you a particular polarization given by the direction in which the charges are moving. Whereas if you have something like the sun, then in the sun what you have is an enormously large number of charges, and they're all going in every which way, because the sun's just a big crazy plasma. So charges will be going in all sorts of directions, accelerating, moving around in that plasma, and so they're going to be emitting lots and lots of electromagnetic waves, but those electromagnetic waves are going to be all in sorts of different directions. And so what you get there is you get a scrambled electric field direction, and that gives you something called unpolarized light. And we often write unpolarized light as having components in all directions. And this interaction between polarization and materials works both ways, not just in emission but also in absorption. So if you have, say, a road and you have unpolarized light coming down on it, say from the sun, so it's easier for that electric field to move electrons sideways on the road than it is to lift them up out of the road and push them in. And so what that means is that light is preferentially absorbed and then re-emitted if it's got that horizontal polarization. So the vertical polarization has much more trouble being absorbed and re-emitted, and so when the light reflects off the road, you tend to have a much stronger component of the horizontal polarization. And that's why sunglasses tend to be polarized. A polarized piece of glass only lets through particular polarizations of light. And the idea with sunglasses, if they only let through the vertical polarization of light, then they're going to make most things darker because most light is unpolarized. So you lose half the light of everything. But when you're driving along, the road glare, the glare from the sun, say, on the road is going to be mainly horizontally polarized. So you lose nearly all of that. That means you're preferentially getting rid of the light that was blinding you while still keeping most of the light from the things you're trying to actually see. And exactly the same principle lets you use the same kind of glasses to see underwater. So if you have light glancing off the surface of the water and that gives you lots of glare and you see reflections, if you put on your polarized sunglasses, you can often see down under the water, which is very good if you're fishing or something like that. So we can describe light as traveling in more or less straight lines for most purposes, and that lets us design optics. We can describe light as bouncing off mirrors and other things that reflects off at the same angle, pretty much like a ping pong ball bounces off a wall. But when we add the wave model of light to things, we can understand details like how it makes interference patterns and diffraction patterns, and also lets us understand things like the fact that it has polarization. And the fact that it's an electromagnetic wave unifies our idea of not just light, but also X-rays and ultraviolet light and infrared light and television signals and Wi-Fi signals and radio and so forth. And so our model of light has got larger and larger and explained more and more. And various approximations allow us to make simple calculations that are applicable in each realm.